couple of times.
Okay, so then I guess you're familiar with how it all works, and so then I'm just going to jump straight into a coding question.
All right.
So first question is, are you familiar with the concept of order statistics? Have you heard that term before?
No.
Okay, it's a very simple thing with a overly complicated name. So given a unordered set of numbers, like what I've written here, the order statistics are like the nth element in the list if it were sorted. So like the first smallest number in this list is going to be 1, and then the second smallest number is 2, and then basically the order, in terms of the order, the nth order statistic is then the nth smallest. Does that make sense?
Yeah.
I guess this is a bad set of numbers to have chosen. So then this makes it a little more clear.
Mm-hmm.
All right, so we're just going to have some algorithmic questions about finding some of these nth order statistics. And just to get started with sort of a warm-up problem, how about if you write a function that, given a list of numbers that are out of order, you just find the smallest. So basically the first order statistic.
Okay. Sounds good. So I'll just declare it here. Public static int is the return. And then I'll just call it min.
Yep.
And this takes int, I'll call it n. All right. So then here I'll
take in yeah, this will be like an array. Yeah. Yep.
Yeah. Sorry. Okay. You know what? Oh, okay. So then I'll loop through the array.
Mm-hmm.
And then for each of those iterations, I'll compare it against a min that I've already set up. So I'll set the min to be ARR at 0. And so what should I return if the array is null, or if there's no values?
Don't worry about the case. We'll just assume it always has some values in it.
Okay, sounds good. So then we'll set the min to the first one, and then going through if the, so then we can actually start, okay, yeah, so then going through to looping through the array, if the element at the index of I is less than min, then we make that the new min. And then at the very end of the for loop, you return min. Yep, so just to test it to make sure, I'll write a little test here.
Sounds good.
So input is equal to, let's see, so like 2, 3, 0, 6 should give us 0.
Yep, sounds good.
Min input, and let's try that then. Oh, I put it inside the for loop. Okay. All right, there we go. So it returns 0.
Perfect. And what's the runtime of this algorithm?
Oh, then.
And is there any faster way that you can do it?
For an unsorted array that I know of, no.
Correct. Okay. So now you definitely got the idea. Now let's make this a little harder, a little trickier. And how about you give me the second smallest number?
Okay. So for the second smallest number, then I think what we would need to do is maintain two variables and then kind of check across both of them to see, like sort of like a larger min and a smaller min or something like that. So then we can check to see if there's a number that's smaller. If it's smaller than both of them, then we'll put it into the smaller min. And if it's only smaller than the larger one, then we can put it into the larger min, the new larger min. So once again, are we assuming that the array's length is 2 or greater?
Yep.
Okay, so then I'll just call this min2, and we'll put this at the second element of the array. And then here, if the array is greater than the min, then it's the very smallest one. So the min becomes array at 1, and then min2 becomes well, we'll do this first. So then min2 should be set to min, and then min is set to the new minimum. And then otherwise, if the array element is less than min2, sorry. Okay, so if it's less than min2, whereas it's still greater than min1, then this means that this should be set to, so then min2 becomes the new element, and then instead min becomes min2.
Min2 becomes the array. Wait, but what happened to min then?
Oh, sorry, yeah, this is maintain the same, I think. Yeah, because if it's less than min2, then min1 is still the smallest, so then that should stay the same, but min2 gets updated.
Okay. Yeah, let's run this.
Oh, I have to return min2 this time. Okay, so this one should give me 3. Oh, sorry, it should give me 2. Okay, there, give me 2.
Yeah, perfect. Okay. Yeah, interesting. I'm trying to think if there is, I'm trying to see if there's a corner case here with the fact, does min2, what if, yeah, I guess, what if these were the numbers here? I'm trying to think. Let's try those out. So so it should actually be 3, because 3 is the second smallest.
Yeah, something like 3.
And so min2 gets set to, I guess I'm just looking at this. What if there were 2? Because you start back at 0 again, and then you flip it all around. I got it. Okay. Yeah. Perfect. Okay. And what's the runtime of this one?
This one is still open.
Okay. So let's just say that we're, as you might have guessed, we're going to want to move this and turn it into n. So we're going to want to add another parameter here that says I want to find the nth smallest. Now, one way you could do it is you could just expand on this idea, and you could just create sort of a list of all of the mins up to n.
Right.
Now, what would the runtime of that algorithm be?
Well, if we're storing them all, then we need to check across each of them each time. So the runtime would become n squared, since we're running through all of the previous values every time we go through the the array.
Yep. Okay. So to get the 0th, or the first, it just took O of 1 or O of n. To get 2, it took O of n. But now if you expand this in that same sort of pattern, it actually becomes O of n squared. So Is there a way that you can improve on that O of n squared time?
All right, let's see. So maybe there's a way where I think one way to improve would just be to sort the array, and then that would make it n log n immediately. And then all you have to do is find the nth index in the sorted array.
Yep. Okay, perfect. Now, here's the real challenge. Can we do better than n log n for any arbitrary? Actually, I guess I gave this the wrong letter. For any arbitrary m that we're trying to find. So we saw that when m is 1, we can do it in n time. When m is 2, we can still do it in n time. Do you think that there's a way that you could extrapolate on that sort of pattern and say, oh, I can just always do it in n time, no matter which one of these I'm trying to find?
Right. So the reason why we could do it in O of n time for if n equals 1 is because we could just go through and compare them all and see whichever one is the smallest. And then for n equals 2, we had to compare it with each of them and also the previous minimum. So, without having to compare it to all of the previous minimums, I'm trying to think if there's a way to figure out the nth smallest. Maybe if we delete certain objects, but then that wouldn't help either, because if we go through.
But if you delete.
Yeah, but that.
So it's tricky. So if you get stuck, I have some hints for you.
Yes, I would appreciate a hint.
Okay, so so you mentioned the n log n case of sorting and then just picking the mth item in the list. So in that sense, once we sort this input, when you have 2, 3, 5, 6, and then let's say your m is 3, and basically you just go straight to the 5, right? And you know that 5 is in the correct place, and that it is that everything to the left is below it and everything to the right is above it, and it's in position number 3, so that means it's necessarily correct. Now, what you've also done, and actually if we expand this out just a little bit more, then then what you can see is 10, 15, and 21. So you had that this number 5 is in the correct position, but also every single other number is also in the correct position. So you've also done work to make sure that the 3 is in the second position, and the 2 is in the first position, and the 10 is in the fifth position, and you've put them all in the right places. even though at the end of the day, all you really cared about was that that 5 was in the right place. Because whatever order any of these other ones are in, it doesn't really matter. You don't really care because you're only interested in this one.
Right. Okay. That's interesting. So basically we're looking for a way to ensure that a certain value is in a certain spot, but all the other values don't have to be sorted.
Correct.
And the one that we want to be in the right place is at the M index.
Right.
So if we did this for the first minimum, then basically we would have to go through each of the elements and then put all of the ones that are larger than a certain minimum to the right of it so that it would be at the beginning. So basically we would have to go through and figure out like how many numbers are lower than that number and how many numbers are larger than that number. So
right.
What if we do that then? Is it like maybe there's some way that we can balance? So say we want M to be 2, like in this case where the index is 2, that means that we want 2 numbers to be less than the one at M and then 4 numbers to be to the right. So then maybe we can sort of like choose, somehow there should be a way where we can go through and figure out and make it balanced so that it's like equal on both sides, even though those aren't sorted. But we would need to know what the number 5 already is in order to go through and actually put that in its right spot. So there needs to be a way where we can figure that out without knowing 5.
Right.
Yeah, and if we just chose a random number or went one by one like we did here, then it wouldn't work because then we would still go back to being n squared. We just still have to go through all the numbers to see which one was right.
Right. But let's take a look at that example that you had just said that you just talked about saying you kind of described this process where you take this input array, you take the first number that you found, and you made sure that it went in the right spot, right? So you described a process of saying, take this number 3 and put it just that one number where it goes, so that everything to the left is less than it, and everything to the right is greater than it.
Binary search tree.
What was that?
A binary search tree?
Yeah, I mean, so there's that's kind of a part of it. But so describe how you might do that. How would you find, so just given, I mean, you don't really have much information about this this array coming into it because it's unsorted. It could be in any order. So you might as well just start with the first number you find and say, I'm just going to put that first one where it belongs, and then I'll tackle the rest of the problem after that. So, for example, you can think of what it would look like afterwards would be 21 and 15. So you can imagine that this might be what the array would look like after you found the first place. So 3 goes in this spot, and everything to the left is less than 3, and everything to the right is greater than 3. And you still don't really know about what's going on either side.